so let's pick up where we left off. We went through a classical argument and some averaging to show how the pressure of the gas depends on the average translational kinetic energy of the molecules. Number of molecules, and inversely on the volume. You try to contain a gas in a smaller volume, perhaps not surprisingly, the pressure goes up. Okay? All right, let's combine that. Nowhere in this derivation did I use the ideal gas law. But since I assumed it's a dilute gas with minimal interactions between the molecules, to also use the ideal gas law must be acceptable, because that's what the assumed are at. So let's combine this with the ideal gas law. Okay? All right, so I should have been, yep, step 3 there in our notes. So now let's combine our result in equation 2 with the ideal gas law. So we'll do that by taking equation 2. Let me just multiply both sides by volume. So pressure times volume just is 2/3 total number of molecules times the average translational kinetic energy of the molecules. And now let me combine that with the ideal gas law. Let me replace PV with the total number of molecules, Boltzmann's constant times the temperature. Okay? So I'll do that on the left. I'll replace the product of pressure and volume with capital N, KB, and the temperature. Capital N, KBT equals 2/3 capital N average translational kinetic energy. Okay? You see, I just took my result from equation 2, and I just also invoked the ideal gas law. Now the ends cancel. And I get a pretty amazing result, that the average translational kinetic energy of the molecules in the box has a very simple form. 3/2 times Boltzmann's constant times the temperature. That definitely deserves an equation number. And it says that if you average the translational kinetic energies of the molecules in the gas, you discover that there is only one thing that affects that result: the temperature of the gas. That's it. Right? That is the only thing that the average translational kinetic energy of the molecules depends on. What's the temperature of the gas? That is related to a more fundamental classical result of statistical physics we're going to be talking about a lot this semester, called the equipartition theorem. That's going to be kind of the conceptual foundation for this result. But you don't need to know that to have derived this. You get it out of some pretty basic physics ideas. Newton's second law for the collisions, averaging, because I only need to know what's happening on average, and the ideal gas law. Okay? So that's a very handy result. That is in your intro physics book, by the way, that result. Okay? Because it's quite striking. The average translational kinetic energy depends on one thing only: temperature. Note something else from this nice result. This is an energy. In SI, you have units of joules. Therefore, since that's a dimensionless constant, 3/2, the product of Boltzmann's constant and the temperature has dimensions of energy. SI units of joules. That combination. That's a really important fact. You'll hear physicists all the time say KBT, KBT, KBT. Okay? You can think of KBT as the characteristic amount of thermal energy that your particles have. Multiplied by a constant, 3/2, is the exact result. Okay? All right, now, that's a really useful result for using the ideal gas law, Newton's second law, and counting. The next thing I want to talk about, so I'm now out to section C, I want to talk about another thing we can get out of this result, what's called the root mean square speed. gas. You've heard that phrase before, root mean square? How many of you heard that before? Root mean square. Okay? So we're going to do the following. We're going to take our new result for the average translational kinetic energy of the molecules. Okay? K translational average is 3/2 times Boltzmann's constant times the temperature. I'm going to replace the left-hand side with another symbolic expression. The average translational kinetic energy is 1/2 times the mass times the average of the speed squared of the molecules. I already have actually said that. So that must equal 3/2 kVt. I can multiply both sides by 2, get rid of those 2's. I can divide both sides by m, and I'll get an expression for the average of the speed squared of the molecules. It will be 3 Boltzmann's constant times temperature over the mass of a molecule. And then let me just take the square root of both sides. Let me just take the square root of both sides. So on the left, I will have the average of the speed squared of all the molecules square rooted. On the left and on the right, I'll have the square root of 3 kVt over m. And then I just recognize that this set of symbols on the left is by definition what I mean by the root mean square speed of the molecules. Because root mean square, there's a case at least, we don't do this very often in physics, so we should acknowledge it when we do. Here's a case where the name really does tell you what it is. It is the square root of the mean of the squares of the speed of the molecules. Right? Take the square root of the mean of the square of the speed. Okay? So that is what's called, as you perhaps know, it's common to write that with the notation VRMS. So then what you have is a nice little formula for the RMS speed of the molecules of the gas. And that's a very handy thing to know. It's telling you on average how fast the molecules are zipping around inside the container. And that depends on 2 things: temperature of the gas and the mass of the molecules individually. Right? With the temperature obviously upstairs and the mass of a molecule downstairs. So if you increase the temperature, apparently they're going to zip around inside the container faster. Doesn't sound too surprising, really. Take out your gas of one species and put in a species for the different molecule, with molecules that have more mass, and therefore more inertia. And the RMS speed for that gas is going to be less. Okay? So that's also very handy. Definitely deserves to be numbered. And let's get some numbers from it. Let's find, so here's a short little mini example. Let's find the RMS speed of nitrogen molecules, N2, at room temperature. What's the RMS speed of the nitrogen molecules zipping around inside this room? Nope, I only need to tell you one thing. What's the temperature? Okay? I mean, you'll have to figure out the mass of an N2 molecule. That's what this would be, yes? The mass of one N2 molecule. But that's just a matter of chemistry. Right? So let's figure out what that is. Little m is the mass of one N2 molecule. This kind of stuff, as I said, I call it chemistry because I need the periodic table. Okay? So what I do is I take what I'll call the molar mass of N2, the mass per mole, and I'll divide by Avogadro's number, particles per mole. And I always figure these things out here when I'm doing this chemistry by units. I just figured it out by units. This is the molar mass. In SI, this would be in units of kilogram per mole, because I know I can get that from the periodic table. And Avogadro's number is particles per mole. In this case, we're talking about nitrogen molecules. So molecules per mole. I'll put molecules in quotes because it's technically not a unit. Just a reminder. Molecules per mole, MOL is the symbol for the unit mole. And then I see, just look at the units. The per moles will cancel, and the units for this ratio are kilograms per molecule. Well, that's what I want. I want the mass of a molecule. Okay. And I want it in SI. I want it in kilograms. So to get that, I get the molar mass of N2. The molar mass of 1N, N, from the periodic table, is 14 grams per mole from the periodic table. 14 grams per mole, but N2 is 2, so I multiply by 2. Okay? But I convert it to kilograms also. Kilograms per mole. So this numerator is 2 times 0.014, write the units too please, kilogram per mole. That's the numerator. The denominator is Avogadro's number, 6.02 times 10 to the 23 molecules per mole. And that number, just to give you, when you divide it out in your calculator, you get the mass of an N2 molecule is 4.65 times 10 to the negative 26 kilogram per molecule. That molecule in the denominator is just a reminder, it's not a real unit. Okay. So I have figured out the mass of a single N2 molecule. And with that, and at some reasonable value for the temperature of a room, I can get the RMS speed of the nitrogen molecules in the room. I don't need to know the volume of the room. Okay? For the RMS speed, the average. Okay? So V RMS is the square root of 3 times Boltzmann's constant, 1.38. times 10 to the negative 23 joule per Kelvin. Let's take room temperature to be 280 Kelvin. Divided by the mass of an N2 molecule, 4.65 times 10 to the negative 26 kilogram. I'm just going to write it like that, kilogram. You can check that the units of all this, once you take the square root of the units inside there on the right, will be meters per second. And the numerical value that you get is 500. 500 meters per second. That's pretty quick. That's the average speed of the nitrogen molecules in a typical room. 500 meters per second. Bouncing off of you right now. Right? Okay. Some are going even faster, because that's the average. Going slower, but some are going even faster. Let's also do one more thing. Let's find the ratio of the RMS speeds of, let's take 2 species of hydrogen gas and nitrogen gas molecules, both at the same temperature. And let's find the ratio. Let's take a species with lighter molecules, right? H2 is pretty light. So I'm going to calculate V RMS for H2 molecules over V RMS for N2 molecules. They could be in the same box at the same time. They are definitely at the same temperature, I'm assuming that. So I will just use this result, equation 4. 3 times Boltzmann's constant times the temperature over the mass of an individual molecule of the particular species you're talking about. But I said that they're in a container with the same temperature. So when I do the ratio, the T factors, as well as the 3 and the KB, they're going to go away, right? And all that this ratio is going to depend on is the square root of the ratio of the masses of the molecules. But the mass of the molecules is going to come from the molar mass divided by Avogadro's number. So really all it's going to boil down to is the square root of the ratio of the molar masses. But it'll be inverted compared to this ratio. So it'll be the square root of the molar mass of N2 over the molar mass of H2, right? This equation for the RMS speed depends inversely on the mass of a molecule. Well, the molar mass of N2, you don't even have to convert this to SI, just keep it in grams, is 28, 14 times 2 grams per mole. And the molar mass of H2 is 2 times 1 grams per mole. So that's the square root of 14, which to 3 sig fig approximation is almost 4, 3.74. So in my sample of H2 and N2, same temperature, the RMS speed of the hydrogen molecules is going to be almost 4 times that of the nitrogen because of their lesser mass. If you took the room temperature situation of 280 Kelvin, you would find that the RMS speed of H2 is 1,870 meters per second. So if you imagine there's a whole bunch of H2 in Earth's atmosphere, there isn't anymore, but maybe there was at one time, an RMS speed of 1,870 meters per second is getting fast enough, at least for the high-end tail, remember that's the average, so some are going faster, that there are going to be enough of them going fast enough that they can escape from Earth's gravitational well. And if you wait long enough, you end up losing more and more of the H2 over time. And so mid-sized and small planets don't tend to retain their H2 over a long period of time in their atmospheres. But nitrogen, which is much more inertia than hydrogen, it can hold the atmosphere, it can retain. Larger planets with a larger gravitational field, a deeper gravitational well, so-called gas giants, can keep hydrogen in their atmospheres. So you find a lot of hydrogen in Jupiter and Saturn, right? So you're starting to learn some of the physics that you need to understand a lot of things. Not just on the planet, but extraterrestrial as well. Okay, so I hinted that this result for the average translational kinetic energy of the molecules in the gas being such a simple result comes from this idea in physics, technically it's classical physics, not quantum, called the equipartition theorem. And I want to start talking about that now. So we're going to use it a lot this semester. So let me start. We're going to go over to the PowerPoint slide here. Yeah.
Why do we pick 280 Kelvin as room temperature? Isn't that kind of cold?
Maybe a little bit cold. You could, a lot of times people put 300. You could do 290. You don't want to sit and shiver. Okay? You could do 290. If you want to really sweat, you could pick 300. I just picked something. Yeah, pick 280, pick 290, pick 300. No physicist will worry if you. Oh, I just mean room temperature. Okay. Okay. Later on in the semester, we're going to prove this expression of equipartition, this result, equipartition of energy. In fact, it's called the equipartition theorem. Theorem means you gotta prove it. Okay? It's one of the few theorems in physics. There aren't many, really, but you can prove it. We'll prove it later in the semester. For now, we're just going to state it and use it. Okay? So here's the idea. It's really equipartition of energy. And equipartition means equally divided. So it's really a result for taking energy and dividing it up equally. Just got to figure out what's the rule for how you do this dividing up. Okay? This is technically valid for a classical system or a quantum system at high enough temperature that it really behaves basically classically. Now, that begs the question, well, how high is high enough temperature in a quantum system that you can treat it classically? Here's the simple back of the envelope answer. The characteristic of a quantum system, that kind of hallmark quantum behavior, is the existence of discrete energy levels. Right? Only certain energies are allowed. And they're called discrete energy levels. And there's an energy level spacing. There's a spacing between adjacent energy levels. In most systems, that spacing varies as you go up in energy. The quantum harmonic oscillator being the classic meaning famous example, where the spacing of all the energy levels is all the same as you go up in energy. But there is spacing between energy levels. Okay? There's a delta E between two adjacent energy levels in a quantum system. Remember, KB times T has dimensions of energy. And KB times T is the size roughly of the thermal energy of a particle in your system. So this system can be treated more classical if the size of KBT, the thermal energy, is large compared to the spacing between the energy levels in the quantum system, the delta E. Because then the thermal energy washes out the discrete nature of the energy levels, and you don't really observe it in the system. Okay? So that's the back of the envelope argument you'll hear physicists give. Right? They say, oh, I mean high energies. Well, what do you really mean by that? I mean KBT is large compared to the spacing between the energy levels. Because that means the thermal energy is overpowering the quantum behavior. So as long as we're in a totally classical system or a quantum system that can be treated classically, that includes an ideal gas, we can use this result called the equipartition theorem. So here's how you use the equipartition theorem. First thing you got to do, you've got to count the number of what are called degrees of freedom that each particle of the system has. And we're going to use the symbol little f to just denote the number of degrees of freedom. So little f will be an integer. And it will generally be a small integer. Say something in the range of 1 to 10, roughly. Okay? We will have to count the number of degrees of freedom f that each particle has. That means we have to be able to figure out how to count degrees of freedom. Okay? So here's my description of what a degree of freedom is. Okay? A degree of freedom is any contribution to the energy of the particle that is quadratic in either a position component or a momentum/velocity component. Momentum and velocity are directly proportional. Just multiply the velocity by mass and you get momentum. So it doesn't matter whether you talk about momentum or velocity. Okay? Position, it's a term in the energy that goes like a position squared or velocity squared. Let me give you an example, completely classical. Physics 110, classical block on a spring, oscillating back and forth on a horizontal frictionless surface. And write down the expression for the total mechanical energy. We would use the symbol in Physics 110, E, and we would say there's kinetic energy and there's elastic potential energy from the spring. The kinetic energy, if the block has a mass m and is moving with a velocity, if this is the x-axis of v sub x, is 1/2 mv sub x squared. And that would be the kinetic energy contribution to E. But because the spring is stretched from equilibrium by some amount I've labeled here x, and the spring has some spring constant I'll label k sub s, then there's also a contribution of from the potential energy of 1/2 spring constant times the amount of stretch squared. So I look at the symbolic expression for the energy, and I see how many terms involve a position coordinate squared or a velocity component squared. And the answer, here's a term that has a velocity component squared, and here's a term that has a position coordinate squared. 2 terms in the energy that have a coordinate or velocity squared. So that system has 2 degrees of freedom. And so for that system, you would say F equals 2. Okay? Just going to have to count how many degrees of freedom your particles have. Why do you have to do that when you're using the equipartition theorem? Here comes the actual statement of the theorem. The equipartition theorem says that if your system's in thermal equilibrium at temperature T, every degree of freedom contributes to the system an average energy of 1/2 times Boltzmann's constant times the temperature. I haven't proved it, we'll prove it later. Right? I'm just stating it now. At temperature T, every degree of freedom contributes to the system an average energy of 1/2 times Boltzmann's constant times the temperature. Really famous result. Gets asked all the time in oral exams in graduate school in physics. Okay? Because it's simple to state. And very easy to use on back of the envelope calculations. Okay? So let's say, for an example, that we have as our system a monatomic ideal gas. Monatomic means that every particle that's zipping around inside the container consists of a single atom. An example of such a gas is neon, and any of the inert gases are monatomic in nature. Okay? How many degrees of freedom does each neon atom have? Any thoughts? How many degrees of freedom does each neon atom have? Go through your mind, kind of thinking like I did right above for the block on the spring. But these are just particles zipping around inside a box, basically not interacting with each other. So, let's vote. How many think it's 1? 2, 3. More than 3 then. Must be the rest of you. Well, if we were to write down an expression for the total energy of a neon atom, I think you're overthinking it. Okay. What's the only form of energy they have? They're moving freely, so kinetic energy. Right? Alright? What's the expression? Kinetic energy. K equals 1/2 m. Now here's what all the intro students say and write. Right? But that's shorthand notation, and it's easy to overlook what that really means. What does that really mean? Well, we're not averaging. This is just one neon atom at a time. But what does that v squared really mean? It means speed squared. What does that mean? How do you find the speed squared from the velocity? It's the magnitude squared of the velocity. So how do you calculate it? 1/2 m times what? Derivative of position, yes. But let's say you know what the velocity is. V arrow. How do I get the speed squared? So what do? Vx squared plus Vy squared plus, right, this is a box, it's got to be 3-dimensional, right? Intro students forget all the time that that means that. All the time they forget that, believe me. Okay? Don't do that. You're at the point now where you don't want to make intro physics mistakes, right? 3 components. So how many degrees of freedom? 3. Because there are 3 velocity components squared. Just count how many terms go like a velocity component squared or a position squared.
And it doesn't apply here the statement that you made before about Vx and Vy is equal?
Doesn't matter. On average, they are equal. When you average over all the atoms in the big box. But I'm just asking for one atom. Just pick one atom. Write down the expression for its energy. That's the expression. All you got to figure out is how many degrees of freedom does each atom have. That expression tells you that each atom has 3 degrees of freedom. Okay? So F equals 3. That's the only thing you've got to think about carefully with the equal partition theorem. You've got to be able to figure out how many degrees of freedom the particles have.
So when you look at it in the average sense, you say that it has only 1 degree of freedom?
No, no. For every degree of freedom, on average, you get this much energy.
Okay.
For every degree of freedom, on average, you get that much energy.
So in general, this will apply to any gas freely moving well.
That's right. Okay. So, for a sample with many neon atoms, remember capital N is the total number of particles, so big N, big value for capital N. Each atom contributes to the total thermal energy of the gas an amount of 1/2 times Boltzmann's constant times the temperature. Remember, 1/2 kBT for each degree of freedom. So multiply the 1/2 kBT by F degrees of freedom. That's the average energy from every neon atom. So the total thermal energy of the whole gas, this would be the symbol we would use, is this average contribution from each atom times the number of atoms. Okay? It's really simple. You just got to make sure you know how many degrees of freedom each particle has. Okay? So we will use this for any ideal gas. We'll use it for other things too. It's valid for anything that's not highly quantum. Okay? We'll give more examples pretty soon. You'll see. So it is important to be able to determine how many degrees of freedom a particle has, i.e. what is the appropriate value of F. That's really the only thing in using the equal partition theorem that can get a little tricky. So let's do an example that's a bit more complicated than a gas with monatomic atoms. How about a diatomic gas? Okay? That's a little bit more complicated. Let's try that. For that, since it's more complicated, we'll go to the board. Okay? So I'm just going on with those notes. Notice I went through step 4 there, so now we're at step 5. Let's consider a toy model of a diatomic molecule. Let's say, for example, H2. Okay? All right, it's a toy model. Works pretty well. We're going to have our 3 coordinate axes, X and Y in the plane of the board. I'll do a kind of a perspective view. The Z-axis comes coming straight out of the board. Okay? I will model the diatomic molecule since it consists of two identical atoms as what's often called the dumbbell model. I'll put it along the x-axis. I'll put one hydrogen atom on one point on the x-axis. I'll put the center of mass at the origin. I'll put the identical second hydrogen atom on the symmetric side of the origin. Okay? The center of mass of the molecule is therefore at the origin. at the instant I took this picture. But it's definitely moving around, and the center of mass might have a velocity, VCOM, for the molecule. The whole center of mass of the thing could be moving. Okay? And because of the bond between the two hydrogen atoms, we model that bond as a spring. Physicists and chemists actually do that a lot. Okay? Well, physicists probably, maybe more than chemists. And let's give that spring a spring constant, K sub S. And in principle, that bond can flex so that the molecules can oscillate back and forth. Okay? And so you've got several things that can happen. The whole molecule's center of mass is zipping, or is, not can, is zipping around inside the box. So I represent that by this red arrow, VCOM. The bond can flex, so it oscillates. The atoms oscillate along the x-axis. And the dumbbell can rotate. And it can rotate about, for this kind of symmetry, about the two perpendicular axes, perpendicular to the bond. It can rotate about the y-axis. And it can rotate about, it can go either way, by the way, about the y-axis, and it can rotate about the z-axis. It turns out if you look along the x-axis and try to see it rotating along the x-axis, there's nothing about those wave functions that will tell you that it's rotating about the x-axis or not. You can't detect that. But you can detect rotation about y, which is perpendicular to the bond, or z, which is perpendicular to the bond. Now that's all the things that can happen. The whole center of mass can translate, move. There can be rotations about two axes, and oscillation about the bond, which is the x-axis. Now I'm going to write down all the terms for the energy that I have from that. Okay? So the total energy. What are the terms that represent? Well, I can have the translation of the center of mass. That's not hard. That's just like this. Right? It'll be 1/2. I'll use a big M. That'll be the total mass. Big M is the total mass of the molecule. So obviously big M is 2 times little m. And that multiplies VCOM x component squared plus VCOM y component squared plus VCOM z component squared, close parentheses. That's one contribution to the energy. I'm going to label it over to the side here. It's the translational contribution to the energy. Okay? But that's not all, because like I said, the molecules can rotate. There can be rotation about the y-axis and rotation about the z-axis. And for that, I just need to also remember some classical physics. There's kinetic energy associated when a body with mass rotates about an axis. And that formula is 1/2 moment of inertia, or rotational inertia, times the angular velocity squared. Well, angular velocity counts towards the degree of freedom, and it's squared. It's squared. That's the key thing. Okay? So let's put it down the rotational part. 1/2 I, there'll be the component of the angular velocity along the y-axis squared. That's from the rotation around about the y-axis. Then there'll be a contribution 1/2 I, component of the angular velocity along the z-axis squared. It's the same I because of the symmetry here. The y-axis and the z-axis are both perpendicular to the bond. The moment of inertia is the same about those two. Okay? You do not have another term with an omega x squared because quantum mechanics doesn't let you detect that. Okay? If it were a more complicated molecule that was like H2O, okay, then you can have 3 axes with angular velocity components along all of them, and you can detect it. But here we have symmetry going, and we're going to stick pretty much, almost all the time, to simple little diatomics or monatomics. So that's it. There are those two, right, from the rotation. So that's the rotational contribution to the total energy. Yes?
So is it just an assumption, more or less, that we, since we can't detect it, that we just neglect it? Because isn't it still a possibility that has cumulative?
But if you can't detect it, then physicists are all about measuring things, right? If you can't measure its consequences, right? And the degree of freedom has to be something measurable. Okay? Question over here.
How do you, like, if you're just given some diatomic molecule, is there a way to know, like, that you can't see?
Look at the structure. This has symmetry along the line.
And that's just, it's not going to.
That's not going to work. In fact, if it's along a line like that, you're not going to be able to see the rotation about that line. And it doesn't even, I think this is true, it doesn't even have to be identical molecules then. It could be CO, I think, right? CO, carbon monoxide. Is CO2 even a linear molecule? Do we know? If it is, then that's going to be the same boat. You can't quantum mechanically detect that rotation about the line of symmetry. Okay? Okay?
For simplicity, whenever we do have a diatomic molecule, do we impose it on the x-axis? So we have
Any axis you want to call it, I just picked X.
So if you want two of the axes to be perpendicular to the bond, so you would never like rotate it because that would make it
No,
difficult.
because nature isn't going to be tricked by us changing our axes, right?
Okay.
Nature is going about, there's a symmetry axis,
Mhm.
and then there are the two directions perpendicular to that.
Okay.
Right? All right, one more set. We have to worry about the oscillation, right? There's energy there too, because that you can detect the consequences of. Here, it's really relative motion, okay, of one atom relative to the other. You can imagine that, well, you're sitting on one and watching the other one oscillate. What energy would it be? It's just like the block on the spring, okay? The notation is just a little bit different. It turns out 1/2 times what's called the reduced mass of the molecule. Mu is called the reduced mass of the molecule. And the reduced mass, mu, is the product of the masses of the molecule divided by the sum. How's that? That's got dimensions of mass. For this case, since the molecules are identical, it's m over 2. Little m over 2. You take 1/2 times the reduced mass times the relative velocity, x velocity squared of one atom relative to the other. And then 1/2 times the spring constant times the amount of that the bond has been stretched, squared, right? I'll write that x minus x0 quantity squared, where the x0 is the equilibrium bond length. The minute details of all that do not matter. Absolutely do not matter. All that matters is, where's my red chalk? That this is the vibrational contribution. And the point is, it's got a quadratic term here and a quadratic term here. Okay? So, 3 degrees of freedom from translation, 2 degrees of freedom from rotation, and 2 degrees of freedom from vibration. Don't worry about that minus x0 there, that's just a constant. Okay? So, 3 from translation, 2 from rotation for H2, 2 from vibration. The only other thing that's a little bit tricky is the following. Well, it's not really tricky, but it's important. You absolutely can never stop the translational motion of a molecule. The uncertainty principle prevents it. You cannot completely stop a molecule. Okay? So these 3 degrees of freedom will absolutely always be active. But these have to be excited by collisions amongst the atoms or the molecules themselves. And if the temperature isn't high enough, the collisions aren't strong enough to excite these. Okay? So these parts of the degrees of freedom, they are only excited by collisions with other molecules if the temperature is high enough. For specifically, we figured this out by measuring the specific heat capacity of your material as a function of temperature. We'll talk more about that Thursday. But let's just say for H2, I will just tell you for H2, that the rotational modes are excited if the temperature of the gas is larger than or of the order of 100 Kelvin. So the hydrogen has to be only warmed up to about 100 Kelvin or more, and the rotation will be active. Okay? To get the vibration, vibrational modes are excited at a much higher temperature. T must be greater than or of the order of 1000 Kelvin. That's because this bond between the two hydrogen atoms is very stiff. So it has a very high spring constant. And it takes a lot of energy to compress it. Okay? So we'll close by saying, making a little table. The number of degrees of freedom F for an H2 molecule will depend on the temperature of the gas. Okay? If the temperature is quite cold, let's say less than 100 Kelvin, then only the translational degrees of freedom are active, and the value of F is 3. If your temperature is between 100 Kelvin and 1000 Kelvin, it's a pretty broad temperature range. It includes, by the way, room temperature, right? Then you've excited translation and rotation, so F equals 5 for H2. If the T is larger than 1000 Kelvin, then you start to excite the vibrational degrees of freedom, and you're up to 7. The tricky part is once you start to get much higher than that, you tend to break the bond anyways. You destroy the very thing you're studying. So it's hard to get up to 7. And if you are given a problem that talks about an ideal gas of hydrogen, and it's at room temperature, the author may not tell you how many degrees of freedom. You'd say, oh, it's diatomic, it's at room temperature, F is 5. Okay? Or they might say it's a monatomic ideal gas. Then what's always the answer for the number of degrees of freedom? 3. Okay? So monatomic and diatomic are the most common. If they say polyatomic, then probably all you're going to do is include one more rotational. Unless it's a linear molecule. Let's say it's not. Let's say it's water, for example, H2O. Then you would have one more rotational, and it's at room temperature, let's say. Then the vibrations are not excited. And you would have an F of 6.
For polyatomic, would the vibrational temperature requirement go up if it's has more?
It depends very sensitively on what the molecules are that are bonded together and the nature, the strength of that bond. Okay? Because it's the strength of that bond that is in essence determining the size of that spring constant.
For polyatomics, would there be more terms of vibrational?
Oh yes, there would definitely be more than 2. But probably most of the time, you're never going to excite those vibrational ones anyways. Unless there's a really, really weak bond. Of course, then again, the thermal motion might break it. But let's say it didn't. If it's a really weak bond, that's the equivalent of having a very low spring constant. That might mean it would be exciting. Now we're getting into the realm of it's highly unlikely we would ever give you this situation. But in principle, you could worry about it, yes. One more question before we go?
Are there any compounds or molecules that have vibrational motion?
I can't think of any common materials off the top of my head. It doesn't mean we might not give you a homework problem that's a Gedanken experiment, right? A toy molecule where the vibrations can be excited at room temperature. Just to see if you can figure out how many degrees of freedom. But it probably would it would almost invariably mean just add on 2 more degrees of freedom. Okay, we will use the equipartition theorem a lot, so you'll get used to it. Yes. Okay. I'm going to talk about that. Okay.
I said I was going to.
That's right, you did it afterwards.
So that day I have like videos and like I have the calculations off the experimentation.
That's all I have.
So laughing.